Okay, so continuing about from where we left off, one interesting thing to point out before we get into things is there's now actually an additional input to the generative node called gap, and the way that's created, and this was pointed out to me by somebody who watched the stream named Cantoran, is you just take anything in your rule set and you wrap it in curly brackets and it creates that input, and it's really, really cool. So I mean, this is like an additional level of parameterization, and I think it's going to be super interesting and fun to play with that. I have not gotten into it yet, so it's totally new to me. And for example, I can just demonstrate add one here, and now we've got that input, and it does whatever it does. I don't know. I've got no clue. Okay, cool. So look at that another time. Really cool to know that. It is actually in the documentation, but I didn't notice it the first when I looked when I've been working on this so far as I've been working on this. So, but I'm glad it got pointed out to me explicitly. So we've got our tree here, and I've cleaned up the file a little bit just on principle, and these are the cylinders that we've instanced as, I don't know, the tree trunks or branches or whatever you want to call them. We're not going to work with those this time. We're going to go back to working with the lines. So let's instance the lines on our matrix, on our tree again. So this here is really what we should think of as our tree, is this output. These are all the matrices that make it up. So we're going to put our lines, actually what we're going to do, because we want to work with these lines, is we're going to apply them, use the tree matrix, apply the tree matrix to the lines. And it's sort of the same but as putting it into the viewer draw node, but it allows us to actually work with them. So, okay, so now we have our lines, and we can, whatever, make more branches. So one thing that we want to do first is note that while this is a really cool structure, it's interesting, it's not actually a shape that appears in nature, and it doesn't look plant-like necessarily. So can we make it look more like a plant? And it turns out that we can, and I'm just going to throw some random values in here, but basically you just adjust these and it'll, well, you'll see, but we'll get some pretty decent results here. So now we've got something that actually looks kind of like a tree. I mean, it's not perfect, and we're going to have to play around with these rules some more to get things better, but it's a start. It's definitely not quite as weirdly unnatural as the original 45-degree or 90-degree angle structure. So we're going to work with this. This is good enough for the moment. We'll, down the road, hopefully we'll figure out how to make them look even better. So at the moment, we have just like kind of tree trunks and or lines. And what I wanted to start doing when I was first playing with this was putting things at the endpoints here. So first of all, because I don't need so many, I'm just going to work with this small structure. And let's see what I mean by instancing something. So for example, we'll take a plane, and instead of applying, and well, I'll show you in a second. Let me get through this. So what we'll do is put the vertex, so let me do this. So this output here, the vertices output, is really each of these points that make up the tree structure. So we can use those, if we just put that information into a matrix input for this plane, it'll put planes in each of those positions. So let's demonstrate that. So let's hit V to connect those up. We got this giant plane. So if we put vertices here, okay, so now we've got something that makes no sense. We've clearly got more planes. The reason is because our planes are giant. So let's make them smaller. Even smaller. Let's try 0.05. And let's bring our lines back. I remember we had this issue in the stream too. I forgot to do this. So I want to see this tree structure as well. Okay, so we now have planes which are sort of leaf-like and a starting point for, say, leaves maybe on our tree endpoints. And that's neat. But the problem is, or at least one of the problems for me was that they're just all straight up. And I want them to kind of be oriented according to this direction. So whatever direction, so they're on the endpoint of this line, and I want them to be kind of facing that direction. Their normal in particular to be in the same direction as the line that as the line they correspond to. So how do we do that? So first of all, so we have all of this information. So we have is lines like L0, L1. I don't know why I'm erasing this, but and then we have vertices. This is V1, and down here it's V0. So what those those vertices are really, we can think of as vectors pointing to those points on the tree from the origin. And so these lines, literally these vectors, are this output right here. So let's just, as I just want to demonstrate this, let's see what happens if we use those directions to orient our matrices. So first of all, though, how do we orient the matrices? So there's a node here called the matrix normal, which it has a location and or a track and an up setting. So it's basically saying for any normal regular matrix, whatever vector comes into this normal position or socket, align the x-axis of the matrix along that. And then I don't quite know how this second one works, but it defines up direction. I'm not quite sure. But I've used xz, and also sometimes z minus z works, although this flips things upside down. So I don't know what just happened there. So let's try to do that first. So that's not the one I want to unplug. So we've got this awful jumble of matrices here, and they're all at the center position. So why they aren't even where we want them, and we can't even tell if they're oriented the way we want them to be. So this is because inherently the matrices don't have any position information. And what we want to do is we want to put them at the locations of each of these vertices. So we put the vertex into the location socket, and now we have, at least they've changed position. We still can't tell what's going on, so the first thing we'll do is take a look at this node and just drop the matrix scale way, way down. And now we can sort of see what's going on here. And the main thing that's going on is that, first of all, these aren't the way we want them to be. This matrix is clearly not aligned in that direction. However, it is aligned in this direction. So what's going on is we've given that matrix this vector, and it's aligned itself with it, and then we've placed it that position, and it's just the issue here is not that Sverchok or the nodes are doing something wrong, it's that we're telling them to do the wrong thing. So what we really want here is we want to figure out what this line is. So we're going to call this like R. And R is a property of the positions of these 2 points, and this is V. So this is 0, 1. And we're going to get confused about the vertices in a minute, but we'll leave that for a moment. So this R vector is actually equal to V2, and I should be putting an arrow on top. So let's just demonstrate that, and so we're on the same page about all that. So, but the basic point is that we want to take this point and subtract this point from it, and that'll give us, and then use that value, the output that we get from that difference, as the normal direction. And then what we'll do is we'll place them on the endpoints of each of those, of each segment. And the first thing we got to do is figure out how to get those vertices. So this is where the viewer text node starts to really come into play. And let's take a look at the data that we're working with and just try to understand it a bit. So what this is I've taken the edges of our lines, the lines output, which basically means the line segments that is making up our tree right now, and I've put them into this viewer text node. And what the output is saying is that line 0, this is line 0, is made up from vertex 0 and vertex 1. Now, then it's saying that line 2 is made up from vertex 2 and vertex 3. So vertex 1 and vertex 2 are in the same position. The reason that this is happening here is because each of these is actually a separate line. So there are 2 vertices in each of these positions. They're just directly on top of each other. So really what we're going to end up doing here is taking this, well, this should be not L2, this should be L1. We'll take this line as R1, and that's actually going to end up being V3 minus V2. So instead of V1 minus V0 or whatever it was that I had earlier. So how do we get that information? So if we look at the vertex output now, this is vertex 0, and then this is vertex 1, and then this is supposed to be vertex 3, which is different from, let's just do it this way. So what's going on here? I don't know. So what's going on? So this is now letting us select by index these vertices. So we can just, interesting. This is all new to me. Oh, they're backwards. Okay. Oh, okay. And this is because something is going on. And it might be, I wonder if it's this. No, that's not. Well, okay. That's the reason. That explains a lot to me. So, but basically, this is line 0. And it's like this is vertex 0, and this is vertex 1, and then this is vertex, and this is line 1, and this is vertex 2, and vertex 3, or something. So they're kind of, we're doing things backwards a bit. Let's pretend that's not going on. What's the effect of that is simply going to be that we're going to have to reverse the direction of our matrices later, but we're going to do this in the same way. I'm wondering if it wouldn't be better to, it might actually be better to do this though. So if we flip these, let's see here. Let's see if we can deal with this problem. So now we just have a simple line. And which one is vertex 0? So let's take a look at this line's vertices. So this is plus y, and that is plus 0.5, and this is minus y, and that is minus 0.5. And so that would make, so this is v0, which means that's v0, and then this is v1, which means that that is v1. So if we flip this 90 degree about y, or x, sorry, so not 90 degrees, 180 degrees, then that should reverse it. Let's see if this actually works. Yeah, I think matrix apply. So I do apologize for this tangent that we're going on, but this is actually, I don't even know that this was happening. So we have to, what was a 180 about the y? So let's just, no, 180 about the x. Right, okay, so keep going, keep going, keep going. Oh god. Well, let's do that over again. I think if you hit hold control, it will like snap. Yeah. I'm doing this just to show what I'm doing here. So now we've got a 180 degree flip, and actually, let's see. So now V1 is over here, and V2 or V0 is over here. Let's see if this works. This is my best guess here at the moment. This may not actually work. I don't know. In which case I'm gonna have to like pause the stream and start over, and I don't know. Right, that's just so we actually want to draw these things. All right, so let's see what happens. Oh, well, it looks a little bit better. Ah, this actually worked. That's really cool. Okay, so V0, V1, V2, same spot because they're the same thing. V3, awesome. I am actually pleased with myself for figuring that out. So, okay, I'm gonna just throw whatever that crap is away. Okay, so now it's actually set up the way I was telling, I'm not lying anymore. Now it's actually set up the way I was saying it is. So this is 0, 1, 2, 3. So what we want, so this is V2, this is V3. So we want this L1 equals V3 minus V2, or whatever notation I was earlier using. Does that actually work? Let's find out. So there's another node, by the way, there's an edge, this thing called the edge boom node, which does what we're about to do. It gives you basically these vertices on the edge, on the ends of an edge, but I want to demonstrate this more explicitly right now, so I'm not going to use it. So instead what we're going to do is we're going to take another list item, take those vertices, and put them in here. Select the second one. Give me a second here. Alright, sorry about that. I got a message that I needed to look at. It was stressing me out. So let's just pull another viewer draw out here, and so we have V2 and V3. Good, that's what we want. So what happens, I don't need to keep moving these out of the way. Let's do a vector math to subtract these. So remember, we want to do V3 minus V2, so we're going to put V3 or vertex 3 into slot A and vertex 2 into slot B. I don't know why I'm belaboring this. And subtract them. Theoretically, that should be that line. So let's plug that into I don't have one because I deleted it, a matrix normal. And we'll try to do our tracking thing again. This actually might work now. Oh, it's because I plugged in with the vertex. So, cool. It's very small, but it actually, where the hell did it go? So we can see it's actually parallel to this. Again, the reason it's not up here is because we haven't told it to be up here. It's just, at the moment it says I'm at the origin because you haven't told me where to be anywhere else. So we want it here at V3. So we'll take this position and use that as the location. Now we can see we've actually got a matrix oriented correctly. Let's see about, this is what I want. Yeah, it's ZX is the right way of doing it. So now we can see this is actually what we're looking for. This is what we're after. So, okay, that's a great start. How do we do it for all of them? Because we want to do this for every single join or every single line segment on this tree. So how? And the answer is some fun Sverchok style list manipulation. So I'm gonna have to figure out how to do this again because I don't have, this is all I've gotten here and all my other versions of this demonstration are in other files, so I'm gonna have to do this. So let's see, what we want here, what we want to do is we want to take the second index and every one of these, remember these are little lines, so we want to take the second index in every one of these and subtract from it the first index. We want 1 minus V1 minus V0, V3 minus V2, and so on down the line. So we can actually pull out the indices, and this is that edge boom node that I was talking about that does this, but I want to show this explicitly. So we can pull out that first, we can pull out all of only the first indices of these lines and only the second ones. How do we do that? We use a list item. We use list item nodes. So I'm just going to cut these off from their thing. Put that in there. This is where the viewer gets really critical to make sure that we're doing what we want. So, and usually it's fiddling, right? I mean, I'm kind of pressing buttons. I mean, I know what this is supposed to be, but I'm usually pressing buttons here to clicking things to get it to do what I want. And that brings up an interesting point, is that you have to turn on this socket menu. This is absolutely critical because this gives you an extra level of list manipulation that we need in this case. And the one we need is flatten in particular. So what we've done here is if we take a look at our original edges list, 0, 2, 4, 6, 8, we've pulled out the first index of all of these lines. So we're going to do that again for the second index. Let's copy that. And this time index 1. And now we've got the second index in all these. So this, we're going to call this endpoint ins for endpoint indexes. And we'll call this start ins. So for each of our lines. So now what we need to do, remember, looking at our lines, just our edges or whatever, we want v1 minus v0. So, and we actually want the vertices. So what we're going to do now is create another of these list items, and we're just going to set it back to defaults. And we're going to use these list of endpoint and starting indices to select for the corresponding vertex. So at the moment this is just a number, but we want the actual contents of the vertex list. So remember, this is v0, v1, v2, v3, and so on. So we want these values in particular, and we can select for them using this list we've created by putting that into the index selection of the list item with the vertexes in the data field. This is giving us some not iterable thing. I think it's because we have to wrap them. So this is more finagling the list. So if we didn't have them wrapped, they're like, see, these items, it treats each of these as an individual thing, and it's one item, so you can't go through, loop through it multiple times. So we need them inside a list. This means it's inside a list. So now what we've got here are all of the endpoint, the positions of the endpoints of the tree. And we can sort of see that if we do this, and the reason it shows up on every point is because, remember, there's those lines not sticking on top of each other. So, but we can see that this is, it's not highlighted here, because that is the starting point of the whole thing, and it's not included in this list of items. So we'll do that the same exact thing to select all the starting line vertices, and we have to wrap this. And we're gonna go ahead and move some of this stuff out of the way. We're gonna go ahead and call this endpoint verts, and we'll call this endpoint, no, not endpoint, starting verts. So what we want to do now is, just like we did earlier, is subtract each of these lists. So these are just a list of, these are lists of vertices now, but they correspond to the endpoints of the lines and the starting points of the lines. But best to just show that this works visually. So we want to take the endpoints and we want to subtract the starting points from them, and then we'll toss that into our matrix normal. And we'll draw that, and we've got this completely, again, as usual, completely wild jumble. Why? Because we haven't given any location. What we want is we want these matrices to appear on the endpoints of each line segment. So we'll toss the endpoints positions in there. And we can see, at least for the first two, things are looking right. Let's go ahead and make those small again to make sure that we've got them right the rest of the places. And we seem to. So that is very cool. Now, why do we, I don't know if I talked about this already, but why do we care about this at all? At this, we still don't even have a mesh here at all, and basically, why do we care about putting matrices oriented a certain way on this tree? And the reason is because matrices are kind of the fundamental unit of position and orientation information in Sverchok, and anywhere a matrix exists, you can put any shape or assembly of objects or whatever, even things you model on top of it, and it will create it in those positions. So for example, instead of just matrices, we can put cylinders at the, or well, you know what, I don't know what would be, what's a good one? I want to use Suzanne, but it's, oh, let's use Suzanne, okay. We're gonna have to scale her down. So we've got a massive jumble of Suzannes here. So I think maybe the matrix deform. So far I've never used this. No. We're gonna do just another matrix of I. Again, hitting V to connect all those up. Trick I learned from watching Arendelle. So this time let's just scale her down. Right, and let's also set this pixel count way down. Now we can actually see what's going on. Also, I'm going to turn off this shading because I don't know how that even happened. Let's try like 0.025 or something. Maybe 0.045. And we have little Susanna heads now instance across our whole tree. So you can do this with anything. And that does include things that you've modeled. So if you take whatever you've modeled outside of Sverchok and you can instance those things with Sverchok, and you can have these matrices, the matrices place that at these positions. So just for visual purposes, I'm going to take Suzanne away and put in like a box or a plane. Maybe a plane is probably the best. And we'll scale these way down. And now we can really, oh yeah, and center them. So now we can really see a lot better, in my opinion, how these are really just really aligned with their corresponding segments. So that's like pretty much, that's like that was like the cool thing that I got to show off, but there's more stuff to be played with here. So for one thing, let me just think, this gets a little bit confusing where you have to do this. So for one thing, if we adjust, we take this matrix, I think. No, it's this one. So let's push this down here. So we can start to do additional manipulations to our instancing matrices. So think of these planes as our matrices. I don't draw them. I mentioned this in the last video. I don't draw them because it slows Blender down like significantly. But just think of these planes are an exact reflection of what the orientation matrices look like. They're just, it doesn't drop my frame rate to draw them. So we'll keep them in here. So if we take another matrix multiply, or it's in a matrix math, and so this is So what we want to think of going on here is that these are our orientation matrices. So just for the purposes of showing it, there they are. So if we can manipulate those further than just getting them to be on the endpoints of the tree and oriented in the direction of them, but we can do things like push them along their, I think you have to set it to post. So we can, no, it doesn't work either. Right, it's going to be Z, sorry. So we can push these along their Z direction and have them move along their segment. I don't know if this is like necessarily something that anybody cares about, but it is something we can control here. I mean, I guess one thing you can do is like have them an animation where they like shoot off or something. I don't know, whatever. But point is, this is a control we have, and this isn't really a great one. So this particular control is kind of just doing all of them. And one thing to note, the thing to notice here is that we can, like, say, just for example, say I want to have each of these matrices at the midpoint of the line they're on. So I've got this tiny movement here, and those are about on the midpoint, but these have barely left the end. And on the other hand, if I get those sort of halfway, now these are just exploded off into space. Okay, so how do we get them to be halfway along their segment? Well, Sverchok gives us a handy node called the segment or the path length node that can help us deal with this problem. So we'll get these vertices. Remember this. So I sort of am. I don't know what to call this, but like these are the matrices that make up our tree. But really, this is now the information we're really working with. So we'll take our vertices from our tree and our edges from our tree and put them in here. And now this node gives us segment, the length of each of these segments. So this is 0.5, this is 0.245, 0.12, and that makes sense just looking at the numbers. So each of these corresponds to one of these planes, and the correspondence is confusing, but it's there. So if we take this and we do just a simple scalar math and take this and multiply it by 0.5 and use that as the position, oh, well, we're going to have to do a little bit more work than that. So we can't just toss this in to the position because it will change the position in all axes. So we only want to do this in the z direction. So we want a vector in node, I think it is. So we don't want to move in the x or the y, but we do want to move in the z. So, and what we also want is we want them to move in the minus direction, negative direction. So now we can see, I'm going to make these a little bit bigger here. Say like 0.2. Let's go with like 0.25. And jumbles up there a bit. Let's go with that. So we can see now that every single one of these is on the midpoint of their line, including, it's like impossible to do up here, including these guys up here. They're also at the midpoint of their corresponding segment. And now we actually have, through this value here, and if we take this and we just invert it, or negate is the command, then this becomes a 0 to 1 range. So if this is 0, they're on the endpoint of their line. This is 1, they're on the starting point. That's hard to see with just the switch, so let's just slide them along. So see this one going down. When it hits 1, it's at the starting point of its line. So this is just a control we can add to our matrices, and you can decide what you want to do with that, if anything. And there's this goes on. We can add rotation scale. We can add or not rotation scale. We can change how it's rotated, and we can start, which I'm going to try and do, which is what I'm working on, and what I'm hoping to put more videos and tutorials and whatever written stuff out for, is like how we can instance matrix assemblies on here. So, you know, instead of just individual objects, have sets of objects be instanced at each of these points, and then manipulate what those, you know, for example, the scale of those objects as they get close to the endpoints. But yeah, so that's future stuff. But this has gone on definitely long enough here. I've mumbled as much as I think I can handle for tonight. So I will put this file online after taking some time to clean it up a little bit, and upload this video when I get a chance. And hopefully I didn't forget to record audio this time. So again, thanks for watching. Sorry for the non-professionalism. Doing my best. Thanks again.